today. Brian did this morning for his proposal defence, and met with the committee, and we had some comments on the material. He's going to go back over it again. We wanted to do it all as one event, but one of the committee is actually on sabbatical in India right now, and we felt that 3 a.m. or sort of 5 a.m. would probably be a somewhat unpleasant event for him to sit through, so we can do it in 2 stages. Brian did his, for those of you who don't know, most of you probably know, did his master's here with us, looking at the fishback multibeam and all the problems included in that system. And we're moving on now to look at what we might do for future generation of multibeams, which would give us significant benefits, we think, over what's currently done, and might solve some problems that we see in the field. And might let us do some really interesting things as well. So, without any further ado, David.
Thank you. Yeah, thanks. Good. Yeah. All right. Hopefully everyone can see. Okay, so imagine yourself surveying in somewhat of a shallow water environment. So we're talking, tens of meters to low hundreds of meters. Because we're in shallow water, you'll be in the 200 to 400 kilohertz range. And so what you got here is a multibeam installed on a ship, and the picture I've got up here, this isn't actually a linear phase array, but for purposes of this seminar, pretend it is. And so the ship's pinging away, and so it pings, and the wave propagates down to the seafloor, all in this insonified area here. Just goes straight down, it does out to these angles, scatters off the seafloor, and the echo propagates back up to the multibeam. So the multibeam does everything you expect it to do. It beamforms, it does time of arrival estimates, and then it figures out when it previously pinged and works out what the soundings are, the sounding depths for each of these beams here. Okay, and so at the same time that it's doing all this, it's waiting to hear the echo. It's also moving along in a long track direction at some velocity. So by the time it gets around to pinging a second time, instead of having a swath of soundings here, this yellow line is a little bit faint because of the lighting. It's not going to be, the next swath isn't going to be at the same location. It's going to be moved forward a little bit in the long track direction. And so this is of fundamental consequence to surveying. A surveyor is going to be surveying and pinging as quickly as possible. And also has this requirement to keep a maximum along track distance between soundings. So there's really only one other thing that the surveyor can do to affect the sounding, the distance between these soundings in the along track direction, and that's to slow down the ship. And so if you slow down your ship, the survey as a whole takes longer, and that costs more money. So it would be a real benefit if there were some way to decrease this along track sounding density, or to increase the sounding density or decrease the space between soundings. The consequence of that would you'd be able to survey faster and save some money there, or you get denser data. But currently there aren't any really good ways to do this. So this is the same sort of situation as the previous slide. You've got time on the vertical axis, and angle on the horizontal axis here. And so same situation, sonar pings. Ping reaches the seafloor. You get your first echo from nadir here, and then this blue line here represents where you'd expect to see the echo. You get the port side over here, nadir, which is straight down and starboard. And if you look at a vertical slice of the echo in and around nadir, what you notice is it's very, very short duration. And the reason for that is you've got a linear phased array, and nadir corresponds roughly on the broad side of the array. So you've got the narrowest beam width at that point. You're projecting it down onto the seafloor at a very small of an angle. So you have the smallest area insonified you're going to get, and therefore that causes this short duration echo. Consequently, if you take a vertical slice over here at port or starboard. Near your maximum angle, it's a lot longer duration echo. And the reason for that is that you're then beamforming out to something like 60 degrees or so. And when you're beamforming off of the broadside of the array, your beam width increases, and also you're projecting onto a piece of the seafloor at an angle, so you get a much larger insonified area, and consequently a much longer duration echo. And so, talked about how you do time of arrival estimation and figure out what the two-way travel time is. And there's a certain assumption that's made when you're doing all of this. And that's that you look at where your echo is, you look back to where you previously pinged, and you say that that's the two-way travel time. And that's true no matter where you are on the swath here. So after you go through and you've listened to your echo out to these maximum angles, which is really your limiting factor here, you can ping again. And so imagine for a second that you didn't have that limitation because you wanted to decrease this spacing between the soundings in the along track direction. You might get something that looks like this. It's still time in the vertical axis, angle in the horizontal axis. You have two pings that are fired off in succession. And you can see the two echoes down here. And what you can notice from this is that although these echoes they'll be seen at the same time, they're coming from different angles. So you'll see an outer beam echo coming in the starboard side from ping 1 at the same time that you see a nadir echo from ping 2, but they're not overlapping, so there isn't interference. And you can still do time of arrival estimation anywhere here along the ping echo. The problem comes in, though, that you can't, the assumption that you can look at an echo and then look back to the previous ping to work out the two-way travel time, it no longer holds. If you're to go ahead and do a time of arrival detection here for the echo from ping 1, look back to the previous ping, which is actually ping 2, you'd work out the incorrect two-way travel time. You'd come up with, you do that for this entire echo here, and you come up with a swath of soundings that's much shallower than it actually is. You'd estimate what the seafloor was incorrectly, and you do this a whole bunch of times. You wouldn't build a map that's actually representative of what's down there. So to look at how we might go about fixing something like this, we're going to look at a single beam, just somewhat arbitrarily at nadir. And this is what you get. Now we've got magnitude in the vertical axis. This is the magnitude of the echo. And time in the horizontal axis. And once again, we've got our two pings and our two echoes. And from something like this, you can't really work out what pings these echoes are associated with. This is it's just an illustrative example, and when you're actually surveying, you're going to be lots of pings, lots of echoes, and you can't sit here and just eyeball and say, okay, two pings, two echoes, I can do it. If you were to want to figure out how to do something like this, what you need to do is construct a coded waveform set. And what I mean by that is that ping 1 would be transmitted with a unique code, code 1, and ping 2 would be transmitted also with a unique code, code 2. And so in this way, you'd be able to tell the two pings apart. Another characteristic of these waveform sets would have to be that the process of you ping and then you scatter off at the seafloor and you see the echo come back, that scattering process would have to not degrade our ability to tell what the different codes were. So we'd still be able to say that echo 1 is of code type 1 and echo 2 is of code type 2. So what we can do at that point is we no longer have to look at the previous ping. We're not saying that this echo right here is a result of the previous ping, because we've gone over that that's incorrect. We look at echo 1 and say, okay, that's code type 1. We're going to look back to the previous ping of the same code type. You'd work out correctly what the two-way travel time was, and everything here would work out. Now this sort of technique, to one extent, has actually been done before. There's some multi-beam echo sounder systems like EM302 that for their code types they actually use different tones. So ping 1 in this case would be a high tone, and ping 2 would be a low tone. And in this sort of manner they work out what pings what. They can see the two-way travel times. And some of these systems also use a little bit of spatial filtering as well. So they'll ping one straight down, and the next ping they'll ping forward a little bit, and that gives them a little bit of processing gain. But ultimately, there's some problems with what's going on here. If you use different tones, you need to use different bandwidths for each of those. So if you have the bandwidth of a multibeam echo sounder, which is on the order of 10% of the center frequency. So for these, the frequency ranges here, that's something like 20 kilohertz to 40 kilohertz or so. You've got to divide that up between your two tones, and that division process where you have less bandwidth for each of the pings means you don't get as good performance. You have less bandwidth, so crummier resolution. Now, if you don't want to sacrifice performance, there's a couple of other things that you can do. You can play some exotic games with your transducers, which exotic in this case just means more expensive. Or you can put a second multibeam echo sounder on the bottom of the ship, and this too is expensive. The total cost of a multibeam echo sounder is significantly driven by the cost of the transducers, so adding a second set of transducers and transmit receive hardware and all of that significantly increases the cost. And it's really this trade-off that gets to the core of my Ph.D. proposal. It's that I want to throw out this idea of using high tones and low tones, and I want to use time frequency coded waveforms instead to get the job done. And by time frequency codes, I mean things like frequency modulated chirps, phase shift keyed sequences, and I want to get away from just two waveforms in a set and move on to 4, maybe 6, or 8, and then consequently be able to increase the sounding density that much. I want to be able to do so with the bandwidths that are available from modern day multibeam echo sounders, so systems like the 7125. There's a whole bunch of them out there that are primarily for shallow water situations. And really the engineering trade-off that I'm getting at here is that we want to trade off cost for complexity. We want to keep the overall system cost down, but we're willing to trade this off with complexity. We're going to have a time frequency coded sets, and there's also a couple of other engineering implications to doing all of this. And so next couple of slides I want to go through are ones that have to do with these consequences and kind of where I'm at in thinking about them so far. So the first thing that we need to deal with is, back to this familiar slide, it's how do we actually figure out that this echo 1 is code number 1 and that this echo 2 is code number 2. And so the way that I'm proposing we do this is that we use matched filters. So for anyone that hasn't seen matched filters before, or just hasn't seen them recently, the way that you construct one is you take the waveform that you expect to see, so a chirp or a phase-coded sequence, and you reverse it in time, and that's your filter. And then you convolve that filter with whatever your recorded echo is. And so when you've got your matched filter that's paired up with your recorded echo of the same type, in this case, what we've got for an example is a recorded echo that's of code type 2, matched filter for and then the associated matched filter for that. The matched filter concentrates all of the energy from that waveform into one point, and the magnitude of that response is very large. Now, when the echo type isn't paired up with the matched filter type, the energy is spread out throughout the signal, and your magnitude is very low. So what you do is you take an echo, you process it through each of the matched filters in the bank, and you look for the maximum response at the output of each of these matched filters and declare that the code that is that echo. Another concern has to do with the fact that you can have echoes that occur at the same time. And the reason why this might be a concern is because when you're out here listening for, you're out here and you've steered your receiver array out to 6 degrees or something like that, you're listening out there for what's going to be a relatively weak echo, and you're very, very sensitive to that weak echo, but you also have to be concerned with the fact that you're still a teeny bit sensitive to echoes that are coming back from here at nadir. And so if you had a very weak echo out in one of the outer beams, and and a very strong echo coming back at nadir at the same time, you might have to worry about that echo appearing as though it was being seen through the outer beam. Now I've gone through and done the simulations out to see that if you're beam steering with a multi-beam that has a 1 degree or a ½ degree or a 2 degree beam width, which is typical of the sorts of multi-beams that we're dealing with here, and you shade the array, and that just means that you're weighting the values of each of the elements to make you even less sensitive to something here at nadir, that it doesn't end up being a problem even in the worst case scenario, which is when you're surveying over a silty, muddy surface where you would expect to see a very, very strong signal at nadir and a very weak signal here out in one of your outer beams. Now another case here, this gets to where I was talking about how you have lots of pings and lots of echoes going on at the same time. Eventually you're going to encounter something where you're not just pinging once and twice and then listening. You're going to be continuously pinging because you need to continuously figure out what the seafloor is. And there's going to be some point where you need to transmit your next ping, but you're also receiving an echo at the same time. And so what that could potentially look like here is that you've got, once again back on time and angle axes. You've got your echo here, and these horizontal bars are representing places where we're blanking the receivers, and that's where we're shutting them off intentionally when we're transmitting so that we don't saturate our preamplifiers. If we do that, it takes a really long time for them to get back to a state where they can listen to an echo again. And so we'll get, if we just shut them off, they'll be able to respond a lot quicker. And this is drawn reasonably to scale in the sense that we expect to be blanking the receivers for a lot shorter the duration than the echo will be, even at the echo's shortest duration. Because we really just need to blank the receivers for when we're transmitting our ping. And here for the nadir echoes, it's going to be stretched out in duration from relative to that of the duration of the ping. So by the time we get down here to some of our outer beams, the duration of the blanking relative to the duration of the echo is going to be pretty small. Now so we want to go through a little bit about seafloor detection algorithms first before we move on, because they affect how receiver blanking does or doesn't affect our ability to do detections. And so typically in these inner beams here, in and around nadir, what's done is because the echoes are so concentrated, you can do a weighted mean time estimate of that echo and kind of look for the center of the mass. That doesn't work so well when you get out to these very, very long echoes where it tends to be spread out over a long period of time. And so if you were to do a weighted mean time estimate out here, your estimate of where the seafloor is would be so uncertain that it's not nearly as useful as if you do this other technique called, it's an interferometric technique. And so if you're kind of from the radar world, you might have heard of it as monopulse tracking. And so what you do is you form two beams with the same array. They're slightly overlapping. You look at the same point on the seafloor, and then you compare the phases in those two beams. And when the phase crosses 0, that's when your echoes arrived at the array. So if we look, we're going to zoom in the next two slides, we're going to zoom into two regions. The first is going to be in the magnitude here, for a magnitude detection. The second one's going to be for a phase detection. So this is the zoomed in echo region, the receiver blanking. And the one thing to note is that this is the echo magnitude here, and it is running in time, but there's also, I've got the magnitude coming out here in the horizontal direction as well. And so this is just some sort of somewhat arbitrary typical echo you might see. And if you blank out your receivers here so that you can transmit a ping, you end up losing all of the information in here. And as a consequence, you can't make that detection. This is unfortunate because we'd like to make detections in every single beam and every single ping, but this is just one of the things that we're going to have to sacrifice to get the additional performance and the additional density of sounds. This is zoomed into the region where we have phase detection. And what you notice is that you have this phase ramp here. And along this phase ramp, what's typically done to estimate where the zero crossing of the phase ramp is you'll make a least squares estimate here, and then you'll compute the least squares estimate, find out where the zero crossing is, and say that's my seafloor detection. If you blank out a portion of that ramp, even if it's at the zero crossing, you can still make the least squares estimate. And the only real consequence at that point is that you'll have a slightly less certain estimate of where the seafloor is. So we have to toss out some of the detections in the inner beams, but we don't have to do that in the outer beams. Combine that with the fact that we're pinging much more frequently, we've got a lot of additional soundings, and that kind of points towards that this is something to pay attention to, but it isn't an automatic deal breaker. The other thing that we could potentially do is, there's nothing that says that we have to ping it on a synchronous basis, so wait the same amount of time in between every single ping, and it may be possible and advantageous to jitter this ping time either forward or advanced a little bit so that we're no longer blanking when we want to do a magnitude detection. We're blanking then either when we're not listening to anything, if we happen to not be hearing an echo there, or maybe down in this region where we're doing phase detection, it's going to be more likely, or we're going to be able to make a detection even though we are blanking. So there's one other design constraint that I've looked at so far, and that's how do you construct the waveform sets? There's certain waveform sets that are going to have good properties with a matched filter bank, and you want to test these not just ideally, but in a situation where you're transmitting from a transducer. And so that's kind of what I did here. I set them in the test tank. It's just in the room over there. And I set up a projecting hydrophone here on the rotating mount pole. I set up a second transducer that was mounted to a pole attached to this plate. Transmitted waveforms, linear frequency modulated chirps, and binary phase shift beat sequences. For anybody that hasn't seen these before, really how you encode the uniqueness of these signals is in the phase transitions. So this is just a sinusoid that then undergoes a 180-degree phase shift, and then another 180-degree phase shift, and then it doesn't undergo any phase shift there, and then does again. And so in this preliminary tank test, what I was doing was I was testing to see what the effects were on my ability to tell from the recorded signals whether I transmitted a code type 1 or 2 or 3 or 4, and I had waveform sets all the way up to 8 waveforms in a set. And what I found was pretty much on par with what I expected, which is as you increase the number of waveforms in a set, it becomes more and more difficult to tell them apart. But at the same time, you can still do that. There weren't any problems telling which echo or which recorded waveform was which code. And so this is really only a piece of the puzzle. It's very preliminary. One of the many things that it doesn't address is how does the seafloor affect your ability to tell, is this echo code 1 or code 2? And so what I want to do to start to dive into that is I want to get down to the pier at Newcastle Island. I want to set up a mechanically rotating mount, put that down underneath into the water, and then look at various pings from different waveform sets, same sorts of ones that I looked at in the tank, at 0 degrees, 15 degrees, 30, 45, and 60. And then I also want to vary a couple of parameters that are going to affect the ability to tell what the echo code type actually is. So things like bandwidth, duration of the signal, the actual waveforms itself, and then also signal-to-noise ratio. And then hopefully through all of this, I'll be able to start to tease out what the various ways in which you might tune a multiping multibeam echo sounder if you were to actually build one. So there's a couple of extra things that I want to do while completing my Ph.D. thesis, and one of which is I need to be doing a lot more modeling. And the reason for this is you can't set up an experiment out in the field that's going to measure every single physical condition. I'm not going to be able to try this with a whole slew of different kinds of transducers with slightly different bandwidths and transmit and receive responses. I'm not going to be able to set this up on every single bottom type. There's only so much variability in the seafloor in and around the pier. And it wouldn't make a whole lot of sense to try to get every single bottom type. So I need to come up with some models that are both going to constrain and inform my experiments from now on. On the one hand, I need to have a somewhat extensive experiment to both test the validity of the model, but then once I'm reasonably certain in the model's ability to predict what's going on in reality, I need to then feed different parameters into the model, like bottom types, various things about the transducers, and say something more universal about what the waveforms are that I want to choose to code with. I also need to really get into what the quantitative benefits of a multi-ping system like this are. Just because you can ping faster doesn't mean it's going to be useful in all situations. There'll be some cases where you can survey faster, there'll be others where you can't. There'll be some cases where additional density is really going to help you out in your automated processing after the fact, and there's going to be other cases where you've got enough soundings to get good estimates of all your points in the grid. So I want to go through and relatively soon figure out where it is that something like this will see the most benefit. And I also need to go through and do a simulation of how often these nadir beams are going to need to be discarded with all the blanking going on. And then also figure out if I jigger the ping a little forward in advance like I was talking about, what's the benefit of that going to be? I need to go through and figure out what the signal processing burden is. How much additional signal processing is going to have to be done to get something like this working. And then I'm also and this is the biggie, is I want to get this implemented on a multi-beam echo sounder. I want to get this prototyped, and I want to be out on a boat with the multi-beam echo sounder installed, pinging away with time frequency codes, recording them, and then doing post-processing to find out how well I actually did in this case. And frankly, this is going to be the sticky one. CCOM doesn't own a multi-beam echo sounder. They might at some point off in the distance. But luckily, we've got a whole bunch of industrial partners that we've got good relationships with. And there's two specifically that have expressed some interest in engaging in sorts of research activities, both R2 Sonic and RESON. And so we're going to be talking with them to see if they'd be willing to loan us a multi-beam, tell us some things about how it works, and with a little bit of luck and a little bit of Larry Mayer, they'll try to rest. Okay, so to summarize, what I'm proposing here is a new method of implementing a multi-ping multi-beam echo sounder. And what I'm doing is I'm getting away from these multiple toned multi-ping systems into one that uses time frequency codes instead. And the point of doing this is to keep the overall system cost down because we're not as concerned about complexity. Grad student labor is reasonably cheap, so I can sit here working away on the problem. The way forward is I'm going to start off with a peer test where I'm going to be finding out some basic information about which waveforms we'd actually want to use while implementing this. Ultimately, the end goal is to get this up and prototype and working using the time frequency codes, using a multi-beam echo sounder up on a ship, perhaps the coastal surveyor. Thank you.
You mentioned interferometric work. Is that you do using the French contours to detect the bottom? Could you elaborate a little more about the interferometric work you mentioned?
Well, it's the same way that you do phase detection on multi-beam echo sounders right now.
How does it work? You have two pings looking at the same location, and you can calculating the interference?
Well, no, it's one ping, two beams. So if you think about the receive array as a whole bunch of elements, You form two sub-apertures and do the beam forming on each of these sub-apertures. And then you look at the differential phase between those. And when that phase crosses zero, that's when they're both saying that that's the time at which the wavefront has reached the transducer array.
And that's on a specific location on the ground? So it's one location on the seafloor?
Yeah, at that point, you're making an estimate of where the location is at one point in one beam.
And can you estimate the coherence according to the interference pattern?
The coherence of?
The quality of the sediment that you're looking at. So if you have a value that is a storm, let's say 100% to zero, if it's like muddy, some fluid mud around, then the quality of coherence would decrease compared to a nice sandy bottom that is strong reflector, because you're getting only one nice scattering pattern.
Well, you are you saying that as a statement, or are you asking it as a question?
I'm asking it. I have experience with radar interferometry, but it's a similar kind of concept of having coherence maps, and maybe it's a suggestion, having coherence maps explaining the quality of bottom detection. So apart from having just a bathymetric model received in radar interferometry from a radar data set, you also have a coherence map saying what's the quality on that specific given seafloor.
I mean, in some ways, I'm going to have to punt on this question since I've only looked at so much data in my time here. I mean, it's done over all sorts of bottom types and works over all sorts of bottom types.
You said you were focusing on the shallow water ones, but the shallow water ones are the ones where you can actually ping at a higher rate relative to the deep water ones. So why the shallow water ones?
A couple of reasons, one of which is the constraints of bandwidth. If you're down at a very, very low frequency, you've only got approximately 10% of your center frequency for bandwidth, it's hard to get enough bandwidth in there to actually be able to do something like this. The other reason is that there's a number of cases in shallow water surveying where for sometimes hydrographic, sometimes for scientific reasons, you don't have dense enough data. There's lots of changes that you want to be observing. And so if you were able to get denser data, then you could survey at a more typical speed.
So deep water, you don't care even if your pings are many meters apart?
A lot of it really depends on the specific combination of what are your beam widths, what are your depths, how quickly can that one ship move. I mean, if you're moving super slow because of a ship constraint, you're not necessarily going to want to be pinging away because ping, your beam footprint may not move much, and so even if you've got more pings, it's just going to be more pings in the same area.
Do you know why industry hasn't done your method? Why did they go the way like the 302 and the 120 with the multiping instead of using real?
Well, I can't read minds yet. But my suspicion is it's more of kind of an evolutionary approach. It's just saying, you need to sit there and you go, well, it wouldn't change much if we just had a high tone and low tone. We could tell those apart, right? And then from there you kind of say, okay, what are the trade-offs of that? How does that affect the quality of the soundings, and kind of work at it from that point. I haven't seen any papers or really heard about anybody using time frequency codes to play this game of how do I work out what the ambiguous range is. They have in some cases used linear frequency modulated chirps in the outer beams, but they're doing that just to extend the range.
Yeah.
They're not trying to tell the ping to ping to ping what the transmit time was.
It's not working too well at the moment.
I heard there's a few
Yeah.
problems with that.
I would ask a question that relates to what Roland asked. I didn't like your answer to his questions, obviously. He said in shallow water, you might want to make more pings and the radio reaches. And I don't, quite frankly, that's the wrong way around. In shallow water, it doesn't take very long to get an echo back, so you don't go very far. Okay, so at 15 meters, say, on navigation depth, at 12 knots, how far do you go off ahead? Decimeter. Who needs anything less than a decimeter? Right? Deep water, most isn't telling you 1,500, you have 15 meters of depth to 1,500, and you travel 8 meters before you get into that. No, it's in deep water you need more atmospheric, not shallow.
To be more specific, these shallow water multi-beams cover the whole range. And I agree with you that you see more situations when you get towards the deeper ranges on some of the smaller boats that can go faster, where you're going to see some of the largest benefit to doing something like this. When you get up into the hundreds of meters of depth range, you start to get more into this situation where you have a footprint that's moving more every single pane.
Totally different question. For some sonars that I've worked with, EK60 and ND70, there's no blinding, so you actually can, dynamic range is so high that you can actually see your transmit pulse. So that would solve part of your problem, but then it brings another problem where you have a very strong transmit pulse at the same time. Have you thought about that case if you were going to implement it that way? And would you be still able to see a very faint echo through a strong, which my gut feeling says no, but maybe.
Yeah, in a case like that, you're trying to fit so many signals in a very small bandwidth that you're not able to have that much discrimination between different codes. So what would happen is if you had your transmit signal and a very, very weak receive signal at the same time, you put that through your matched filter bank, and you go, oh, I see the signal that I transmitted, surprise!
So it would be just the same as blanking,
Yeah.
essentially.
Yeah, if you had vastly more bandwidth, you would get more processing gain from your matched filter, and then depending on what the relative magnitudes were, then you might be able to approach it from that standpoint. My gut feeling, though, is you have to have one heck of a bandwidth to be able to listen to this very, very, very faint echo in the same bandwidth as this very strong signal.
Any more?
Have you found anything in the literature from radar on these kind of techniques and how they're implemented and how some of the problems that you described have been solved or worked through?
Yeah, there's a whole slew of cases in radar and a couple in medical ultrasounding as well, where they use these time frequency coded waveforms to get better resolution. That's specifically in the ultrasounding. They'll use things like an up chirp and a down chirp to get better resolution on the images that you see. And then the most analogous case in radar is where they'll have a couple of radar in the same area that are transmitting at about the same frequency, sometimes legally the same radar type. And they need to come up with a set of waveforms so that when one radar transmits and then you get the electromagnetic wave that goes up and scatters off of a plane or a missile or whatever, you're not just going to get scattering back to the radar that transmitted, you're going to get scattering back to all of the other radars in the area, and you need to be able to differentiate and say, okay, that was me, so I know where it actually is, otherwise you won't be able to do things like tracking or even just basic detection. And so when you get into phase-coded sequences, all of the really, really awesome research that I've been reading about is coming from people that are designing radar signals for exactly these purposes.
And in your work in the tank, did you record data that would allow you to see whether or not you can detect your signals and distinguish between them from reflections off the tank bottom or the side?
I haven't gotten into this. The tank experiment was really to answer the questions that I already spoke to, and then also there's a whole bunch of things that you figure out when you actually get your hands dirty and set up an experiment, and you start to work through some of those.
Is there anything in the literature, in the acoustics literature, about how likely a coded waveform is to be distinguishable after a reflection on different kinds of sediment?
Tangentially, yes. And the places that you see this are in underwater communication. If you're dealing with very, very long baselines, you're going to get reflections off the sea surface and the sea floor. And so they'll use things like phase-coded or amplitude-modulated sequences. And then they've actually got a trickier job. They need to say not just which waveform from a set is this, but they need to distinguish each and every single phase transition. And they're able to do this successfully So this gives me confidence that there's nothing about the reflection or scattering process that's going to destroy the information in this waveform. It's going to muck it up a little bit, make it harder to see what it is, but the basic information should still be there.
Anything else?
Do you foresee some difficulties with platform motion? The PFM sweeps on the conference, I know they have to compensate for the vertical motion during the transmit and receive. So Doppler shift in the signal, you're going to have to, is that going to interfere at all with what you're doing?
I would expect that we'll have to compensate for it because it's going to affect the ability of these matched filters to do their job properly. If you have a frequency shift in your echo, you're not going to get the signal then that you're convolving with your matched filter isn't going to be the same, and it's going to behave in some ways that you don't want it to. But at the same time, for multibeam echo sounding, you're measuring the motion of the ship anyway, and so you should be able to work out what that Doppler shift is, and then apply that in any sort of matched filter processing that you have.
I want to compliment you on your summary, but I see a lot of humor in each one of those statements, but I'll save it for later. Definitely, yeah, that's good.
Okay. Questions? All right.
Back drive for area and